The paper, titled "A Post-Hurricane Building Debris Estimation Workflow Enabled by Uncertainty-Aware AI and Crowdsourcing," addresses the challenges posed by managing large amounts of debris after hurricanes. Accurate debris estimation is crucial for effective disaster response, cost reduction, and minimizing health risks. Traditional debris estimation methods rely heavily on manual, time-consuming processes prone to human error, which hinder rapid disaster response and cleanup efforts. The authors propose a novel workflow that integrates drone imagery, Bayesian neural networks, and crowdsourcing to provide faster and more accurate post-disaster debris estimation. The workflow begins with drones capturing aerial images of affected areas, followed by an AI model that uses Bayesian inference to predict damage levels and estimate the resulting debris volume and composition. To further reduce uncertainty in AI predictions, a crowdsourcing module is incorporated, allowing human participants to provide calibrated damage assessments, which the AI uses to refine its estimates. A case study of Hurricane Laura, 2020, is used to validate this approach, demonstrating that the human-AI collaboration reduces estimation errors, particularly for moderately damaged buildings. The combined approach significantly decreases the time required for debris estimation, potentially from days to just a few hours, and reduces prediction uncertainty by up to 40%. The results highlight the potential of integrating AI and human inputs in disaster response strategies, optimizing debris management, and improving resource allocation during recovery efforts.